Hi, I am Hyun-Ju Jeon from the Korean Institute of Atmospheric Prediction Systems. Our system called CloudNine is designed to provide analytical insights for optimizing the use of meteorological observations, addressing the challenges in weather prediction caused by climate change. Current weather forecasting relies on numerical weather prediction systems, which use three-dimensional physical models and dynamical equations. The increasing frequency and intensity of extreme weather events pose significant challenges to accurate weather forecasting. Therefore, one of the effective solutions is to develop observational strategies that effectively utilize the limited observational equipment and the computational resources. To this end, techniques for quantifying and analyzing the impacts of observations on weather forecasting are essential. Meteorological observations are irregularly distributed in a continuous space, and numerical models make predictions using three-dimensional grid points with regular spatial temporal intervals. To effectively analyze their correlations, we propose the web application called CloudNine, which allows users to analyze the impacts of individual observations based on the explainable graph neural networks and interactive visualization tools. Here are two related works. The first is the OC system. It is the traditional data denial experiment with and without some of the observational data. However, it is computationally expensive as the number of experiments. So it focuses only on the importance of the types of observations rather than individual observations. Another approach is the FSOI system, which allows to quantify the impact of observations using the adjoint matrix of the NWP equations. Despite its effectiveness, the FSOI system is difficult to apply to different NWP system due to its high complexity and dependency on the specific system. In conclusion, we clarify the existing studies have limitations to provide tools to meteorology researchers to analyze the impacts of individual observations to weather predictions at specific spatial temporal regions in detail. Our previous research has successfully analyzed the importance of different types of observations, but we have not progressed to developing applications that allow users to interactively analyze the impact of individual observations at multiple spatial temporal resolutions. As shown in the figure on the right, our CloudNine system can interactively visualize XGNN results, allowing a comprehensive assessment of how individual observations influence weather forecasts within a specific region. In addition, by analyzing the importance of observations at different resolutions, we can provide valuable insights that actively contributes to improving observation strategies and forecasting system. Here is an overview of the CloudNine framework. It is an overview of the developed interactive web application that combines an XGNN-based AI engine with a traditional numerical engine. First, we need to build a meteorological data set to combine observational data distributed in continuous space with the NWP data organized in the three-dimensional grid. We define the meteorological graph that represents the spatial adjacency relationships between the two types of data samples. The dataset comprises observational and grid points data sourced from the Korean Meteorological Administration. Among the various types of observation used by KMA, we utilize totally 11 types of observations, including ground and satellite-based observations. In the meteorological graph, spatial adjacency between nodes is determined by the 50-kilometer radius proximities. And temporal adjacency between nodes is determined by a 1 hour interval proximity. Then the AI engine uses meteorological context and analyze the observation impact by using the explainable graph neural networks methods. The features of each node in the meteorological context are reconstructed, capturing the relationships between neighboring grid points and observations. Finally, node level regression is performed using the updated node features to predict current atmospheric states. Then the system applies an explainable method to reveal the impacts of each node on the predicted atmospheric states. We aggregate the impacts from multiple meteorological contexts associated with a single observation to produce an average impact. Finally, the user interface facilitates the visualization of observation points and observation impact, providing a comprehensible representation of the model's insights. Users can interact with the system to analyze the impact of individual observations at multiple spatiotemporal resolutions. We build the system with Python, Flask API, Viz.js, and Vocale.js. Here is our demo video. The first web page that users encounter when accessing the system provides brief information about our CloudNine system. At the bottom of the page, users can directly select the location and time they'd like to analyze. Now we know which grid point can be predicted using observations. Points activated in red indicate grid points that have observations as neighboring nodes. By hovering the mouse, we can check the node ID and basic information of each grid point. And by searching in the input box below, we can check the meteorological context of that point on the map. This is a preview page to check the actual location of grid points and observation points on the map. However, 3D data is distributed vertically. Therefore, if we want to check the meteorological context in more detail, we can click the button below to search the meteorological context in the form of a subgraph. After checking the meteorological context, we can run the AI engine by clicking the button. The importance of the node on the map is represented by node size, and the color of each node represents each types of observations. All nodes were the same size in the preview, but in the result view, we can see that the size have changed depending on the node importance. Finally, the aggregated impacts of all individual observations can be viewed by clicking the final buttons. This page contains a bar plot showing the importance of its types of observation traditionally showed in meteorology. The most key contribution is that the importance of each observation can be viewed on map at high resolution. Each node represents an individual observation, and we can check the observation type, impact, and brief information by hovering the mouse over the node. Mouse over the node. The purpose of this study is to provide an interactive tool to analyze in more detail the impact of individual observations that have previously analyzed broadly. Thus, by analyzing the Bayesian characteristics of the particular observation or the characteristics of neighboring observations, we can contribute to the development of the specific observation use strategy. Thank you.